Okay, great. My name is Chung. I'm a principal with Leers Weinzapfel Associates in Boston, and I think I might be the lone Massachusetts representative at this conference, but glad to be that, if that's the case. You could always tell it's the last session of the multi-day conference because the energy level's a little bit down, so I'm going to try to share a lot of pretty pictures and renderings and minimize my talking and get you guys through this presentation. So what I'm basically going to share is really, in essence, the last year and a half of my professional life in the next 30 minutes, okay? So the project that I've been involved in is the Integrated Design Building. It's the home of the design disciplines at UMass Amherst, Department of Architecture, Landscape Architecture, and Building Construction Technology. And we think this is the first composite CLT building in the United States. I might be wrong, so if I am, please don't hold me to it. Just a little bit about our firm. We're a small to mid-sized firm based out of Boston, about 30 people. And we've been in the business about 30 years and have had the pleasure and the honor of doing a lot of well-publicized buildings. But in terms of doing mass timber structure, this is our first building, and it's under construction right now. So when we were told that the project was going to be mass timber, we were like, okay, this is a great opportunity, but we know nothing about mass timber. This is about 2.5 years ago. And so we solicited some contacts for who were the experts in mass timber. Really, the driver of this project were academics from the Department of Building Construction Technology, Peggy Clausen and Alex Schreier, and I'm sure many of you guys know them. The timber industry is a very small industry. And I asked them, okay, we need a great structural engineer who's an expert in timber construction, and who do I go to? So he gave me a list of 3 firms. And at the top of that list was Equilibrium Consulting, Robert Molchek. Contact him. So we did. And this is how the story starts. And I always joke to Robert, and Robert's sitting in the audience over here, I said, you know, if Alex and Peggy put you guys down on the second and put some other firm on the first of the list, this might be a different story here. I say that as a joke, but of course, you go and do your research, and you know, I was just floored by the buildings that they have done. This is their work with Michael Green, the Wood Innovation Forum, and the Ontario Gallery of Art with Frank Gehry. And what really struck me was that unlike most of the buildings that we've done in our past 30 years, which were steel and concrete structures, which at the end of the day often gets covered over by drywall or other finishes, really with mass timber structures, you can't separate architecture and structure. So really the need for the architect and the designer, architect and the structural engineer to work together in concert is paramount, because where architecture begins and ends and where structure begins and ends is really assimilated. And I think that's the point, and that was our goal, to create a project where architecture and structure could work in concert. So I'm going to talk a little bit about the introduction of the project, set up the background and the context, the design concept. Then really the meat of the presentation will be about the process. How does the architect and the engineer work together to create a mass timber structure? And then not only in the design process, but in terms of code approvals, assuring the client, mitigating risk, procurement, code review and variance, all the less fun part of the designing process as an architect. How do you do due diligence in that and make sure that all of those really real-world issues are accounted for? And then the last part will focus on the central space, which we think will be the highlight of the project, and how we came together in creating the central commons and the courtyard above it. And then some few construction photographs in progress. So in terms of the context, Amherst is in the middle of western Massachusetts. It's a rural environment, and you can see at the distant background there with several tall buildings coming up, that's the campus. And then as we started the project, we took a lot of inspiration from the region in terms of the landscape, the agrarian patterns, the forest, the western Massachusetts, but also indigenous structures, such as at the top here, the tobacco barns, which were beautifully crafted, structural examples of timber buildings, the real original timber buildings. Looking at the campus, and I'm just going to ask you guys to just focus on the pond in the middle of the picture there as a point of reference as I go through the next several slides. The three departments that were going to be now joined together in this building were spread out across the campus: building construction technology at the north end, architecture and design in the middle, and landscape regional planning towards the south. And the goal was to really bring these departments together so that new synergies and collaborations could take place, so that the advancements of research and teaching and learning in a collaboration and that method could really be fostered by the building. And the site was right at the nexus of what we call the main campus, the larger buildings that you see on the left there, which is the grid of the main campus. And then just to the right of it, the original historic part of the campus with smaller buildings. So this diagram quickly shows the importance of the site. The building really is located in between these two different scales of the campus, the larger scale to the west and to the smaller scale and brick buildings to the east. And the challenge and the idea was to really, how do you make a home for the building that's just not about the internal programs, but then it starts to connect the campus together, the old historic part of the campus and the new part of the campus. And we arrived at a solution that what we call is a lifted up courtyard. It's a courtyard building that has a center, a common core that everybody could come together, but then we lift it up and reveal it so that the campus could be invited into the building and partake in the activities of the building. So simple concept diagram, taking the traditional typology of the courtyard, which is great for that, having that common core, but also it's inherently interior in its original form. And then using the geometry and the campus siting to really break open that courtyard and lift up one end to respond to the scale, but also let the campus into the building. At the very early on, the central space, there were dueling, visions of that space. Some faculty members wanted it to be a central space that was a tall 3-story atrium so that it could be a space that everybody could gather. The landscape faculty wanted a beautiful courtyard on top of it as well, and they wanted that to be the feature. So we married those two concepts, and here's just a sectional diagram of how the building works. It's a building of studios and offices, which are located on the upper levels with the big classrooms and the various digital fabrication lab, wood testing lab, and wood shops at the bottom. And the 2-story common space links those first and second floor stories, and then the courtyard, which sits on the 3rd floor, then interacts with the space below through skylights and other means. So putting that together in the sectional perspective, you can see that the 2-story space is really at the center, connecting all the activities of the building with the courtyard on top. And the site, as it goes down towards the west, it's about a 6-foot difference. The building form rises as well to address the scale. So some images of the building. And you can see the first floor opened up and seeing into the building itself. As the form rises toward the west, and then a smaller scale on the east side of the historic part of the campus. So in terms of the design process, this is a picture I think that's familiar with everybody. In Boston, it's a steel industry. Predominance of steel is everywhere. And the challenge was, in this environment, how do we successfully complete this building of a new typology in this region? And early on, we looked at several different massing options, irrespective of whether this was going to be a timber building or a steel building. And I would say that if the mandate was, from the beginning of the project, was that this would be a timber building, we might have looked at a less complicated form. The building would have been a very different building. But that mandate wasn't there. It really actually, as I get to tell the story, about 3/4 of the way through the design development is when we got the mandate to go to timber structure, which was a challenge in itself. So, and very early on, we just had a notion that maybe we could afford or it would be nice to have some sort of a wood structure in the middle. And this is a structural plan, a schematic design. This was done in steel. And I would say that looking backwards, really, I think the fortuitous thing and the kind of the pre-planning was that we knew that there was a slight chance that this might go to timber, although all the risks and the budget and everything wasn't played out by then. So we said, okay, let's have Robert and let's have Equilibrium come in, and while this is being designed in steel, let's design it also in timber, so that big things like column grids, spacing, the spans, those things could be accommodated cost effectively in timber should this switch. And that was, in hindsight, that was a great thing to do. Because otherwise, if we didn't account for that in the beginning, and as the project turned to timber at the 3/4 through the design development, it would have been a redesign, and we were able to avoid that. So in contrast, here's the structural diagram at Schematic Design, a very early 3D model that was done based on that. And then as the building got a little bit more articulated, this is in design development, steel framing, and then in contrast, timber framing. And you can see that in contrast, there's a lot more beams in the steel building. And this is using a typical metal deck. And with the spanning capability of CLT, a lot fewer beams are needed. So this was one of the pleasant surprises that we found out. I'm sure Robert knew this all along. And this is a Revit model that our office did, looking at the structure. And in terms of looking at the cantilever formed, you can see that where we have transfer beams and cantilevers, we did use steel beams. So as much as we are excited about mass timber, we also want to make sure that you're using materials properly. You use timber where it's necessary and needed and where it makes sense, but where you have cantilevers and other things where steel is better, you use steel. And then obviously the foundation is concrete, because the concrete does that better. So looking at the diagram of the building, the plan, concrete foundations, the shear walls, all the cores, the stairs, the elevators, the shafts, those are all in CLT shear walls. And then we have the post and beam superstructure of the building with CLT floor panels with concrete on top. And then the central space with what we call the zipper truss, which we'll explain later. So really this was our mantra, was that the change is possible everywhere, that the typical assemblies in steel that everybody knows, all of that can be done in timber. So steel post and beam goes to glulam post and beam. Concrete masonry shafts can be done in CLT shafts. Steel concrete floors can be done in CLT concrete floors. Steel deck could be done in CLT roof panels, and steel braces and glulam braces. So these were a series of pictures from precedents that Equilibrium had worked on before, and this was instrumental in really educating the client, the code officials, as to what type of building that we were proposing. So this is a beautiful, clean connection between a typical column and beam. And, and we told the code officials, you have type 4 construction, which is in the code, and you see this here. You have a solid timber and a traditional exposed steel connection. How much better is that we cover up that weak point where the steel can melt in a fire, where the glulam here, in this case, the heavy timber, could protect that connection. So using Sherpa connections and other hidden connectors, we're able to do that. And we were able to show also that concrete cores can be done just as easily in CLT cores, and the savings that you get in terms of the lightness of CLT as opposed to concrete, 1/6 of the weight. And then we showed previous testings that were done with a composite floor assembly with wood, insulation, and concrete, and using a very proven and well-tested system of perforated metal connectors to have that composite action. And we settled on a HPV connection system developed out of Germany by Leander Baton. And we were able to show that what we're doing is really no different than what you have right now in typical steel construction, where you have metal deck, Nelson studs, and concrete. We're doing the same thing in timber, that's all. This is a view of the UBC building that Equilibrium had worked on, where the floor is almost all set for concrete to be poured in. And again, not different than a typical steel building with metal deck, rebars, and wire mesh before the concrete gets poured. So, and then a view of the CLT roof panels being put on, which is no different than steel deck. I should say not different in the sense that these are proven assemblies, but much more efficient and much more time saving in the field because of the panelization. So I think as we were able to basically take mass timber and all the components of it in this building and just say, you know, these may look new, but in a sense, they're doing the same thing that you're all accustomed to. I think that paradigm shift was key in really getting the inspectors on board. But, you know, also we had to do, I'm just going to pass through the Glulam Bracing. But in addition to that, we had a project where we had a lot of stakeholders. The client, the UMass Building Authority, the user client of the UMass Amherst, the 3 departments that were there, our structural team of our office, Equilibrium Consulting, and a local structural engineer of record, and then your authorities having jurisdiction, the state building inspector, board of appeals, as well as the team of construction manager, timber fabricator, and installer. And so these are all complex components of what happens when you actually have to build a building. And it was a lot of work. We relied a lot on Equilibrium because of their expertise to provide reports and all the testing data that was done before. We touted the sustainable benefits of timber structure and why ecologically, environmentally, this was the way to go. And then we also looked at the key issues of the important issue of money, right? When it comes down, a lot of times, it comes down to money. That's just the fact of building and this industry that we're in. In terms of bidding and procurement, what do you have to watch out for? The danger of overestimating and having a blown-up contingency because people are not aware of the process. The importance of having multiple bidders, where in steel, you have anybody can do it. There was a multiple of choices. But at that time, the fabricators were limited, especially in North America. The coordination of fabricator and installer team, that we could have a single source to rely on, so there would be no finger pointing back and forth. And then proper scoping of work for bids, especially in this case because the selection of the fabricator installer was done while the construction documents were were under progress. And then also looking at the contractor and subcontractor reputation and history. It's a small world, everybody knows each other. So after schematic design, we solicited estimates from fabricators, and we had 3. And that allowed us to make a comparison between timber structure and steel structure. And I would say at that point, it was about a $2 million difference that the mass timber structure will be $2 million more expensive. And that's counting the overall project cost, counting for the soft costs, as well as a proper amount of contingency, and all the factors that are listed before, that there's a shortage of, you don't have as much competitive bid, things are unknown, you have to mitigate risk, all of that. And then by the time we got into the actual bids at the halfway through construction documents, that list of bidders for fabrication and installation was expanded to 8, among which we've got 6 bids, and then we settled on an eventual fabricator of Nordic out of Canada. So in terms of the code review and variance, again, we did a whole prescriptive performance-based alternative structures approach, and looking at CLT roof floor panels and shear walls, which we said was coming into 2015 IBC, so that was a point of assurance for the building officials, pointing to all the guidelines that were already standardized and in place for CLT construction and all the various requirements of that. And then looking at the floor panels and glulam beams with composite concrete, and really we listed all the various metrics, where it was done before, all the experience, the testing, all of that. And it was really about, at the end of the day, our alternative structural systems report that we had to hand in for the variance process was probably about 300 pages thick. A lot of it in European, which was translated after the fact. And we showed examples of testing of the strength of CLT floor panels. And then in terms of the code and variance, we classify this as a type 4 construction because given all the unknowns, this was the best way to, in our building, to progress forward. It was not a high-rise, 3 to 4 stories, so that was a sweet spot in our case. And the one area that we had to account for and get a specific variance was the requirement for no concealed ceiling spaces, which type 4 construction has. And we had to say, okay, there are certain acoustic issues and utility issues that we have to cover some spaces, and we limited that to 20%. So things like drop ceilings and acoustic ceiling tiles were limited to 20% there. Now, the last part of the presentation, I want to just focus on the central commons and the courtyard design. So this is a rendering of our central space, what we call the zipper truss. And the challenge was, on top of that, this is what the clients wanted, a full-blown landscape courtyard with intensive and extensive green roof. When I told this to Robert, Robert was like, oh. I think his response was, okay, they want to do what? They want to put 18 inches of soil everywhere? So that began another challenge in terms of not only working with myself and Robert, but also working with the landscape architects and trying to reach a solution that would preserve the integrity of the steel and glulam zipper truss below, but also accommodate the needs of the landscape faculty for what they needed to do to demonstrate green roof technologies on the roof. So again, there were opposing design parameters here. Maximum planting was what they wanted with minimum maintenance desired. They wanted the heaviest weight on the longest span. We wanted an open atrium, but had to have minimum structural height for obvious reasons. It's a wet garden on a wood structure. And then again, no direct load path on one side because we wanted this to be a column-free space along the main central stair. Initial design for the central courtyard was a lush garden. Plan of that there. And when we were looking at that originally, we were thinking, okay, this is kind of a concrete structure, heavy structure. This was before it went to mass timber. And at the time that I engaged Equilibrium about the design of the central space, we really wanted that basically we knew that there was a component of both intensive and extensive green roof, but also skylights to visually connect two spaces and bring natural light into the space below. And we went through a series of various structural strategies for the central space. And what we settled on was at the bottom left-hand corner there, what we call the zipper truss, in which we found a nice precedent that we liked in terms of an overall structural strategy that could work well with the column grid and the rest of the architecture of the building. And we went through a series of different ways to do the zipper truss and settled on a very, I think, what I'm hoping to be is a very elegant system that is also very rational. Taking the space and getting the span and just basically dividing it into thirds, and then the compression loads in the middle go down to the diagonal compression members, which then get transferred back to the column ends where they're supported by tension rods. And we looked at that and we studied that in a physical model very early on. And then we looked at, what does that mean in terms of the most ideal place to put the loads for where do you want the heaviest planting and the soil loads. And obviously, given that structure, it's the perimeter and where the beams are and away from the center. But we really, in order to get the garden-like feel, you needed this much soil. So there was a lot of coordination and discussions back and forth, and we were able to reach a solution in which we preserved the garden feel, the notion of the lush landscape, but then also put most of the heavy planting, the smaller trees, things like that in the perimeter and the area where there's the shortest span. And we tested that in a physical model. And a view of that in the plan of that in construction documents. Again, the rendering of that space above and the zipper truss space below. And looking at the development and the design of the zipper truss, this is our rhinoceros model. But all of that, again, we started out with basic sketches between Robert and myself. Again, using our hand and working out the basic concepts of the various connections. We looked at a plate connection at the beginning, Then we needed a more mass to concentrate all that load as all the loads converge at the central point. We looked at a sphere, which we could do that, but didn't like the shape of it and the heaviness of it. And we settled on what we call a bullet form, which was a more slender form that still allowed all of that forces to go through. And then looking at it in more detail, you look at how and ways to save money to make these in components, repetitive members. Looked at existing systems that would then be connectors, so that not everything had to be custom. And then the way we also set up the model was, again, everything that we have as architects and designers in our tool, from our sketching, physical modeling, but also the latest software. This is a parametric script from Grasshopper, where we were able to make these parameters for the different components of the zipper truss, so that as Equilibrium and us, we went back and forth in terms of looking at the member sizes. What if the diagonal rods were not 10 inches, but 8 inches? The tension rods 2 inches instead of 1. We could just put these parameters in the model, and that we could instantly see what the change was, and we didn't have to wait a day. We could just have somebody do it, and then in our conference calls and conversations, make that decision together and efficiently. So this is a very final Rhino model detail, reflected ceiling plan of the zipper truss, and then some sectional views. And by doing it this way, we were able to visualize, but also make sure that exactly in terms of how we wanted the joints to be made were documented in construction documents, so we owned all of that scope. So in conclusion, and this is something that I went in being very hesitant about. Is this really possible? Am I getting over my head here doing a mass timber building for the first time? But I'm glad to say that no, change is possible everywhere. This is the rendering that you've seen before, and just 2 weeks ago, that same view as a structure is being constructed. The central space of the courtyard, which that same view has been constructed now. The floor of the courtyard isn't there yet. The main view, where you can see the diagonal bracing in prominent view and not hidden from the outside. That's being under construction, the bracing there. A view of this CLT shear walls with cantilevers, and you can see the steel beams clad in wood for the connection of the CLT panels to that. Underside of that cantilever. Some of the joint details, hold downs for the shear walls. And then in terms of the composite floor construction, here it is with the CLT panels, which we had the perforated mesh installed on shop. And then this is with the insulation after that was installed. And then a layer of mesh, and then the final product with concrete being poured. And then just some details of the beautiful, really elegant, simple connections that's possible. So I just wanted to say thank you for the opportunity for me to speak on this project.